All right, we are going to continue our discussion on the mixture of liquid. And if you remember, in the previous lecture, we've talked about mixing perfect gas as well as mixing a liquid that is called an ideal solution. If you remember, the important message from the previous lecture was that when you mix perfect gas A and B, so let's say you have a binary mixture, A plus B, and both A and B are perfect gas. When you mix them together, we've derived and we've learned that the Gibbs energy of mixing is always a negative number. And the origin, and this tells you that mixing of A and B is a spontaneous process, and it's thermodynamically favored process. We know that Gibbs energy of mixing is a sum of enthalpy of mixing minus temperature and mixing entropy. And we've also learned that when you mix a perfect gas, you don't really have change in the enthalpy. And that is because for a perfect gas, the interaction between A and A is negligible, or you don't have any interaction. You don't have any interaction between B, and also you have no interaction between A and B because they are all perfect gas. And therefore, in terms of enthalpy, that is mainly determined by the interaction between the molecules, you don't really have any change even if you mix A and B, or if you have A and B separately. So this term was equal to 0. Whereas when you mix A and B, it's pretty obvious that the entropy is going to increase because now before mixing, they were presented separately. They existed separately. When you mix them, you shuffle them, and therefore the entropy of mixing is going to be always larger than 0, regardless of any composition. And consequently, because temperature is always a positive value, you always end up with having a negative Gibbs energy of mixing. That was one important lesson from perfect gas. And then we've talked about a liquid mixture. Now A and B are liquid, and of course, for liquid, there are finite interaction between A and A, right? If you don't have any interaction, you can't have liquid. So different from here, the interaction between A and A was 0, interaction between B and B was 0, and interaction between A and B was 0 for ideal gas. But for liquid, this is not going to be 0. Interaction between B and B is also not going to be 0. And you're going to have interaction between A and B. But when I say I have an ideal solution, I'm telling you that even if these interactions are non-zero, they are all equal, right? That's basically what ideal solution is. And as a consequence, what you're going to have is, if you think about Gibbs energy of mixing, same as that. If the interaction between A and A is equal to B and B and A and B, then you're going to have no enthalpy change upon mixing material A and material B, right? So this is going to be, again, equal to 0, regardless of the composition. Whereas if you think about the entropy is going to always increase when you mix them, right? And therefore, this is always 0, and therefore you're going to have a negative Gibbs energy of mixing regardless of composition for A and B. And that was called an ideal solution. Now we are going to, and in this case, we've also, right, and in this case, we've learned that, oh no, never mind. Right. So the topic that we're going to talk today is now a real solution. And of course, real solution is going to be different from ideal solution. And you're going to have, I'm going to talk about mixture, A plus B. And there is going to be interaction between A and A. Of course, this is going to be non-zero. There is going to be interaction between B and B. And of course, that's non-zero interaction. And I'm going to have interaction between A and B, of course. This is not going to be zero. But different from here, where we had same interaction between A and same interaction between B and B and A and B, the interaction here is going to be different. And this interaction is also going to be different. And in this case, if we define this again, if we define the Gibbs energy of mixing, if we define the Gibbs energy of mixing, things become a little bit more complicated, because now the enthalpy change upon mixing is no longer necessary equal to zero. It can be zero, but it can also be, it can also be non-zero, right? It can be zero or it cannot be zero. It really depends on how A and B interacts with each other. So when this is not necessarily zero, and we know that even if it's a real solution, when you mix them, this is going to be always a positive value. And this term here, the first term here, can be positive value, it can be zero, or it can be a negative value. And depending on this, or depending on how A and B interacts with each other, and A interacts with each other, and B interacts with each other, this term is going to be determined. And as a consequence, the Gibbs energy of mixing can be, the overall Gibbs energy can be a negative value, it can be equal to zero, or it can be equal to positive value, or it can be both negative value or positive value, depending on the composition of your mixture. So things will get complicated, right? And we are going to talk about this real solution more in detail. And before we discuss about real solution, I'm going to define what's called an excess function. And basically, the excess function describes the deviation from ideal behavior. It describes how much it is different from ideal behavior. So for example, let's say I have an excess function x, or an excess function of x. This means x in ideal case x in real case minus x in ideal case. If excess function is zero, it tells you that it behaves like ideal material, right? So when I define excess entropy of mixing, this is basically the mixing of entropy change in the mixing minus, and for real solution, minus entropy change upon mixing of ideal solution, right? The excess enthalpy is defined as, for mixing, is defined as enthalpy change upon mixing minus enthalpy change upon mixing for ideal solution. And we know that this is equal to zero for ideal solution, and therefore that's going to be equal to enthalpy change upon mixing. If you think about the volume, or the excess volume, that's defined as volume change upon mixing minus volume change upon mixing for ideal solution. And we also know that this is equal to zero, and therefore that's equal to mixing volume, right? So that's excess function. And I'm sorry, but I'm going to define another solution that's called a regular solution. I know that they sound, well, they look similar, but regular solution is in fact one of real solution. This is one of many possible real solution, right? Right? Any solution that deviates from ideal solution is real solution, right? And one of real solution we're going to define as a regular solution. And for regular solution, the excess enthalpy is non-zero, of course, because there are interactions involved. But for regular solution, the excess entropy is defined as 0. So a solution, this is a real solution, and therefore the change in the enthalpy of mixing is non-zero, but the change in the entropy upon mixing is just same as how it was for ideal solution, right? So I'm going to consider the interaction factor in terms of enthalpy, but when I estimate the entropy, I'm going to treat my mixture as an ideal solution, right? That's what regular solution is. So if this is true, mathematically, we can say that entropy of mixing is just as entropy of mixing of ideal solution, right? And how do we present the excess enthalpy? The excess enthalpy now is going to be a non-zero value, or is going to be, we're going to define this as n times, I don't know what this is called, RT XA, XB. Of course, XA is composition of A, XB is composition of B, or the mole fraction of A and B. R is the gas constant, T is the temperature. This parameter, I just forgot how to pronounce it, but let's just call this, what should I call this? It's squiggle for now. This is a dimensionless parameter. Dimensionless parameter. And this basically describes interaction between A and B, describing interaction between A and B. What do I mean by that? This dimensionless parameter squiggle can be a negative value, and it can also be a positive value. But if this is a negative value, it tells you that that's negative. These are positive values, and therefore it tells you that excess enthalpy is a negative value. It tells you that basically mixing is, so it tells you that there is a typo in my lecture note. It tells you that mixing is exothermic. And why is that? So let's think about a case where you have an interaction. Let's say you compare interaction between A and A, interaction between B and B, and you compare this with interaction with A and B. If you have a negative excess function, if you have a negative mixing in the enthalpy, it tells you that the interaction between A and A or B and B are stronger than interaction between A and B. Because interaction between A and B themselves are stronger than A-B interaction, they are happier when they are separated in terms of enthalpy, right? Because you have more favorable interaction between A or among A's, and you have more favorable interaction between B and B. You don't want, in terms of interaction, you don't really want to interact, right? Because interaction between A and B are so small. And therefore, if you, I'm sorry. Not true. When you have an exothermic process, I'm sorry, the interaction between A and B should be much stronger or stronger than interaction between A and B, right? Because interaction between A and B are stronger, A and B want to interact with each other rather than being surrounded by A themselves or B themselves, right? So interaction is favored, mixing is favored based on enthalpy. And in this case, if you mix them, change in the enthalpy is going to be a negative value. And this is going to be negative value, and therefore excess enthalpy is going to be a negative value. And in order for the excess enthalpy to be a negative value, your squiggle, dimensionless parameter squiggle, has to be a negative value, right? And if this is a negative value, the consequence is that if you think about the Gibbs energy of mixing, determined like this, you know that this is now negative value regardless of the composition. And we know that for regular solution, mixing of entropy is equal to mixing of entropy of ideal solution, which is always a positive value regardless of composition. So this is always a positive value regardless of composition. And therefore, Gibbs energy of mixing is going to be a negative value regardless of composition. And it tells you that mixing occurs spontaneously at any given composition, right? Let's think about the opposite case where you have a positive squiggle. This now tells you that excess enthalpy is a positive value. In this case, it tells you that mixing is endothermic. What I mean by endothermic, I'm telling you that when you mix them, the enthalpy increases, right? And that happens when interaction between A and A or B and B are much stronger or favorable compared to interaction between A and B. The interaction between A and B are not so favorable. They don't like each other, and they would rather exist separately. So they don't want to be mixed. And therefore, if you compare the entropy between before mixing case and after mixing case, you would find that the enthalpy is going to increase, right? Now, things become more complicated because now if you think about Gibbs energy of mixing like this, and in this case, for regular solution, this is going to be always larger than 0. This is also larger than 0. And then what about the Gibbs energy of mixing? It really depends on how large this is and how large this is. The sign really depends on how large this is and what your squiggle value is. So you can end up having a Gibbs energy of mixing, negative value. You can have positive value. This can also be 0, and they will all depend on the composition. So in this case, you cannot state that mixing would occur spontaneously no matter what. You do have to think about the condition that you have. So let me describe this using a graph, or a graph that you may be more familiar with. The y-axis is the excess enthalpy. Well, let me divide this by nRT for as a normalization, and this is going to be for regular solution. we know that this is equal to enthalpy of mixing divided by nRT, and I have a composition of X, or mole fraction of X here on the x-axis, mole fraction of A in the x-axis. This is 1, 0, and 1 here. Now, if you have a positive squiggle, of course, excess enthalpy would look something like this. It can be a large positive value, it can be a small positive value, it can be a very small positive value. But if this is a positive value, the excess enthalpy is going to be always a positive value. If you have a squiggle being equal to 0, that's the case where you have 0 excess enthalpy. If you have 0 excess enthalpy, if this is 0, I'm telling you that that's 0, and I'm telling you that my solution is ideal solution, right? In this case, that's going to be ideal solution. And you can also have a negative squiggle. It can be a very negative value, small negative value, or a value very close to 0, right? So that's what you have. And now let's think about the entropy of mixing, right, over a given composition. And we know that from perfect gas or from ideal solution, we know that the entropy of mixing would increase, or would be a positive value that looks like this, regardless of composition that we are talking about, right? This is always a positive value. And now what we want to do is, with these, now we want to find Gibbs energy of mixing for different composition from 0 to 1. Now, let's first think about this case here. This case here, where we had a negative squiggle or a negative excess function here. In order to calculate this, what we're going to do is we're going to have n squiggle RT XA XB, which turns out to be the excess enthalpy, minus T. What was the relation describing this behavior here? It was really minus NR XA log XA plus XB log XB, right? I hope students all remember this. Then it's the math here is really NR log XA log XA plus XB log XB, right? That's what you're going to do, and therefore what you're going to do is you're going to add this blue curve here with this curve here. Of course, you're going to have a negative sign, and therefore you're going to I'm sorry, you're going to add this with negative. You're going to add this blue curve here is really this part of the equation, and this curve here is really this part of the equation, and you're going to have you're going to multiply this by negative T, right? And therefore, regardless of composition, if you do the math in the case where you have a negative squiggle, you're going to end up with a curve that looks like this, right? When you have negative squiggle. What about if you have squiggle being equal to 0? If that's 0, this term is equal to 0, and when that's 0, you're going to have 0 excess enthalpy, and therefore all you have is really this term here multiplied by minus t. It's going to be slightly larger value than this, right? And for both cases, it tells you that regardless of composition that you have selected, they are all negative values. Mixing of mixing of A and B are thermodynamically favorable if you have ideal solution, or if you have a solution that has a positive squiggle value, or I'm sorry, negative squiggle value, right? But now let's think about case like this. Let's think about this case here, where you have a positive squiggle and where you have unfavorable interaction between A and B. They don't like to be mixed. Even if the entropy tells you that mixing would increase the entropy of your system, interaction-wise, they don't really want to get along, right? In this case, if you do the math, what you're going to do is you're going to have a positive term here added to this term here. And this term here was shown in the red curve here. Now you have an extra positive term. So this curve, if this squiggle is a very large value, this curve can be a positive value, right? The overall value can be a positive value if this is very large. And it tells you that regardless of composition, Gibbs energy of mixing is a positive value. And it tells you that they don't want to be mixed, right? If the squiggle is a positive value, but not as large as it was here. So let's think about case like this, for example. So you do have a positive squiggle, you do have a positive excess enthalpy, but this is not so large. In this case, you're going to have a curve that may look like this, right? Because you're going to add this a purple curve on top of my red baseline here that was determined from here. And in this case, even if the interaction between A and B was not favorable, they didn't really want to be mixed. However, if you mix them, the entropy of your system increases, and therefore that's really the driving force that makes the mixing of A and B possible, or a mixing of A and B to become spontaneous. So even if you have an unfavorable interaction between A and B, they can mix spontaneously. Now let's think about a case in the middle, like this. Now you have a squiggle value that is not as large as here, but not as small as here. You have a medium squiggle value. In this case, what you can have is you're going to add a term that is not as large as this, but not as small as that. And you can have a composition that a curve that looks like this, right? What does it tell you? It tells you that Gibbs energy of mixing can be a positive value, and it can also be a negative value. Let me draw this in separately. It tells you that I had a relation like this for composition. If my mixture is 1-to-1 mixture, half and half A and B, it tells you that Gibbs energy of mixing is a positive value. They don't want to be mixed. But if my composition, for example, is 10% A and 90% B, Gibbs energy of mixing is a negative value. They will be mixed. If my composition is 80% A and 20% B, I have a negative Gibbs energy of mixing. They will be mixed. So in this case, mixing will be determined, or whether A and B will be mixed or not is going to be depend on the composition you have, right? When it's close to 50%, they don't want to be mixed because the interaction between A and B the non-favorable interaction between A and B is dominant factor in determining the Gibbs energy of the mixing. Whereas in this case, you still have non-favorable interaction between A and B, but what you gain from entropy by mixing A and B is is larger, and therefore Gibbs energy of mixing is going to be a negative value, right? Right? Any questions so far? All right, let's move on to the next topic. We're going to continue our discussion on mixture, liquid mixture, A and B, or binary mixture. And we're going to talk about the interesting properties of liquid mixture. And especially I'm going to talk about liquid mixture where I have much larger mole fraction of A and very small mole fraction of B. And in this case, I'm going to call A as my solvent, and I'm going to call B as solute. So the mole fraction of A is going to be much, much larger than mole fraction of B in this case. And in this case, I can also call this as dilute solution because the mole fraction of B is just so small, right? I'm going to describe interesting properties that is determined only by the number of solute. Properties that are determined only by the number of solute. What I mean by this is I'm going to talk about these properties that is not determined by what type of solute I have, but the properties that is determined by the number of solutes, or the quantity of solute, not the type of solute. And these properties are called colligative properties. And I'm sure that students have learned this somewhere. And the four properties that I'm going to talk about is the lowering of vapor pressure. So I'm going to compare the vapor pressure of a pure substance A and the vapor pressure of A added with tiny amount of B. And what I'm going to tell you is that as you add more B into A, the vapor pressure is going to go down. And I'm going to explain why that happens, right? I'm going to talk about the elevation of boiling point. So I'm going to compare the boiling point of a pure substance and the boiling point of pure substance added with small amount of B. And I'm going to tell you that depending on how many number, or depending on the moles of B you added to A, the boiling point is going to increase. And it's not going to be determined by what type of B you added, but it's really going to be determined by how many number of B you added into A, right? That's colligative properties. I'm going to talk about the lowering of freezing point. And finally, I'm going to talk about osmotic pressure. Right? And when I do these discussions, I'm going to assume that solute, which was B, the tiny amount of substance that it added in the mixture, solute B is non-volatile. What I mean by that, let's say I have a mixture of A plus B in the liquid phase, right? I have a dilute solution. I have a plus B in the liquid phase, and I'm going to talk about equilibrium, this liquid being in equilibrium with the gas phase, and I'm going to claim that solute B is non-volatile. It does not evaporate. So I'm going to neglect the chance of B existing in the gas phase. I'm going to claim that solute is non-volatile. I'm going to also claim that solute B does not dissolve in solid. So for example, if the temperature goes down and down, A plus B, this liquid is going to freeze, right? It's going to freeze and it's going to become a solid, but I'm going to tell you that only A would freeze. And in the solid phase, I'm going to claim that there's no B added in the solid phase. And this is what I mean by solute does not dissolve in solid. When I make a solid, it's going to be pure A. Those are my simple assumptions here. And I'm going to describe all these in terms of chemical potential that we have learned, right? So let's go back to chemical potentials of pure substance and mixture in liquid. Let's think about chemical potential of A in the liquid mixture. If I'm talking about a pure substance where XA is equal to 1 or pure, we agree that we're going to claim this is equal to mu A star for liquid, right? That's how the star was to describe pure substance, right? But if they are not pure, or if they are really in the mixture, and let's say XA is not equal to 1 anymore, but let's say this is an ideal solution. And for ideal solution, the ideal solution follows the Raoult's law, and therefore the chemical potential of A in the liquid phase in the mixture is going to be the chemical potential of A liquid star plus RT log XA. That's what we've learned, right? If you have a mixture. And we know that XA is less than 1, no matter what. That's going to be a negative value, no matter what. And therefore, this term here, which was a pure chemical potential of liquid, should always be smaller, should always be larger than the chemical potential of A in the mixture, right? This has to be always smaller than this value. This is A in the mixture. And that's A pure, right? When you have a mixture, you have a lower chemical potential. And as a consequence, let's draw a plot that we have seen so many times. Chemical potential of A and how that depends on temperature, or you can think about Gibbs energy here. We know that the slope between chemical potential and temperature is a negative S, if you remember, and we drew this type of a plot so many times, right? This was for solid, this was for liquid, this was for gas phase, and from this we conclude that because at least over this temperature range, substance preferred existing in the solid phase because that's how to minimize the Gibbs energy, or that's how you minimize the chemical potential, right? And over this temperature range, the substance prefers to exist in liquid phase because that's how you minimize the Gibbs energy or the chemical potential. And at this temperature range, the substance prefers existing as a gas phase because that's how you minimize the chemical potential. And this temperature was known as the boiling point. This temperature was known as the melting point or the freezing point, right? And I've just discussed that for a liquid phase, the chemical potential of A is lower in the mixture than it was in the pure substance. And because I have assumed that solute does not exist in gas phase, or solute does not exist in the solid, the chemical potential of A in the gas phase or in the solid phase is not going to change, but this curve is going to change as you mix them. And this value is going to be lowered. And let's say this is lowered to here. This is going to be lowered, and how much it is lowered is going to be determined by RT ln X8, right? And this is always a negative value. That's now lowered. And as a consequence, the transition between this curve, this line and this line occurs now at here. The freezing point is lowered, right? The boiling point here, the transition between this line and this line occurs now at here. The boiling point has increased, right? So you can describe these two things or two observations simply based on the lowering of the chemical potential as you mix this with a substance B. Why does that happen? Why does that happen? Why is this lower than here? Let's think about this way. If you have a substance that has if you have a pure substance, the entropy of your system is going to be low, and therefore the tendency for my pure substance to change into a situation where you have higher entropy is going to be strong, and therefore you have a larger chemical potential. But if you have a mixture to start with, the entropy of your substance is already large, or maybe large enough, that the tendency for my substance to change into another situation is going to be lowered, and therefore my chemical potential is going to be lowered, right? Does that make sense? Entropy of the mixture is larger than entropy of a pure substance. And therefore, if the tendency is to increase the entropy, you really don't have a large enough motivation for a mixture that has already a higher entropy to reach a state with higher entropy right? And therefore, the chemical potential, what was the chemical potential? It was basically the potential for my material to do something crazy, right? But my material already has higher entropy to start with, and therefore, it doesn't really have that much motivation to go even crazier because it's already crazy, right? Whereas for pure substance, it's very pure. You have low entropy to start with, and therefore it has this large motivation to become crazier, right? That's sort of a qualitative description of what we had. And let me do this. Let me describe the colligative properties using equations.